Let's talk about iterative refinement. Don't confuse iterative refinement with iterative methods. Especially don't confuse that when doing your exam. What is iterative refinement? We don't introduce a new algorithm as we did. We introduced LU decomposition, column pivoting, total pivoting, QR decomposition, iterative methods. These were all solvers for a system of linear equations. Now we will use one of these solvers and then we try to improve that solution, the produced solution. What is the idea of that? Apply one algorithm of your choice, for example LU decomposition with column pivoting, and then you will find a solution. But in reality, this will not be the solution. It will be some approximation to the solution. And now we want to improve this solution. How can we do that? We can multiply our solution with A, and then we can take the difference to B. If this solution is completely correct, this would be the zero vector. But in reality, it will not be the zero vector. And then we have an idea to improve. And what is the idea? Take this difference as the new right-hand side instead of B. And how do? We once again use our algorithm which we have chosen before. If we have the QR decomposition or the LU decomposition, we don't have to decompose once more because we only exchange the right-hand side. This is an application when we save a lot of time if we only exchange the right-hand side. But that is not the really important point in that video. It's only some remark you should not forget. Apply our algorithm again to solve that system, but what shall we do with that solution? It has nothing to do with our original problem. No, it has to do. Let's see. Let's assume it's completely the correct solution of that. That is not realistic, and we will write down here what do we have to do. But for the moment, to better understand the concept, then this is the correct solution. Why is that true? We can test by multiplying, and let's use the rules for matrix calculus. So we can multiply A times x1. And what is A times x1? A times x1, bring that to the left hand side, bring the D on the right hand side. So A times x1 is B minus D. And what is A times x2? It's the solution of that, so this is D. B minus D plus D is B. So indeed, this is the correct solution as we have seen here. Okay, let us first assume is correct. There will be again rounding errors. So what will we do? We will iterate that process. Because this assumption is not correct, so we can do in reality, because this assumption is incorrect. So we can once again calculate a difference. Now we can calculate the difference B minus A times this solution, and then we solve again. We take this D as the right-hand side and we get a new x3, and then we add x1, x2 and now x3, and then we will get an improved solution. And as I said, we can iterate, so let's write down one more step and then I think it's clear for everybody. Okay, and if this was D2, then we should write here D1. Okay, we can do that, D1, but we can also don't do that, and let's keep it as it is. One important thing, we don't want to go too much in detail, but this is really important. these operations, this one, this one, this one, these operations should be executed with double the accuracy as the solver uses. So if 64 bits are used for the operations, for the LU decomposition and so on, then for this operation here, here and here, we should use 128 bits or even more, but at least double the accuracy. Okay, so let's have a look in my script. Here is that section, and I wrote on the paper everything what is here. And here we have an example. Let's use a matrix 100 by 100. Let's disturb the 10 block as we have done before a lot of times. This block, we exchange the numbers by very small numbers close to 0. And then let's use a solution, calculate the right hand side so we know the correct solution in advance. Then multiply the first 10 lines, these 10 lines, together with the right hand side b by a factor which is a large factor, and then call a solver LU decomposition with column pivoting. And we know that our matrix we constructed here causes a lot of problems for that algorithm. Here we can see how bad the solutions are, and then we iterate, in this case, fixed 20 times iteration. That's also this. Here we go to the symbolic toolbox. That's the double accuracy. So it's a big gun here. This does not work in Octave as I saw preparing for that video, but in MATLAB it works. So we get a completely correct D, and then we solve with the exchanged right hand side. Now we use D instead of B. Having that, we add the X we had so far in the new one, and then we can check how good is our solution, how far away is our solution X from the correct solution we knew from before, because we did that. And then we see in the beginning we had 0.0162 as the deviation, so it's not too bad. This has to do because last time we used 2 to the power of minus 50, now we use 2 to the power of minus 40. So we get a solution which is not too bad, but it's bad. And then after one step we get this deviation, which is much better. And one step later we get this deviation, which is much better. This deviation much better. This deviation much better. This deviation almost perfect, and then the solution does not improve any more. And so we see we can't improve it to infinity, but that is absolutely no problem, because if the entries are between 0 and 1 of the solution, then an accuracy of 5 times 10 to the power of minus 14 is almost perfect till the last digit. Almost perfect. Okay. And how can we check when to stop? We can use that XD. We can take the norm of this XD, and if the norm of this XD and the next one is in the same range, here from here to here it's not in the same range, the D shrinks by a factor of 1 divided by 1000 or something like that. But if it stays in the same range, then we should stop the iteration instead of doing that 20 times. Okay, then in that case we will not do that, and this, having our solution here, our algorithm will stop. Okay, this was an interesting idea. When I first heard of it, I was a little bit confused, because I've not expected that we can improve a solution by applying the same algorithm again. But it really works. And that has to do with more or less taking out the first digits out of the calculations, and then we can focus on the last digit. That's more or less the principle idea behind that concept. Okay, this was our video about iterative refinement.